Hello everyone, let's continue with our course on HCI storage. So first of all, we've already covered two topics before, which are the development of storage architecture and the evolution of storage media. Today, we will officially talk about interface protocols, specifically the development of interface protocols. First of all, the interface protocol. What is the interface protocol? What is this interface? What is the interface? In fact, it is the interface of our hard disk. That is the hard disk interface. Here, everyone should first pay attention to the fact that when the hard disk and our host want to communicate, it is like this. That is, we are a hard disk, and we have a cable coming out of its interface. Through this cable of the hard disk, we connect to our server or other hosts. So, who does it ultimately connect to? It mainly connects to the memory. In general, the hard drive is primarily interfacing with the memory. When it comes to speed, we've talked about this before, right? Memory is the fastest. In the same price range or at the same level, memory will definitely be faster than all hard drives. In this case, especially considering the many different types of hard drives we've discussed earlier, for example, if I want to use one in a server, all hard drives need to be fast. In this case, in fact, especially like we talked about many different types of hard drives before, right? So let's say I want to be on a server. Can I use many different types of hard drives? Yes, you can. This actually brings us to the issue of interface protocols. Specifically, what kind of interface protocol we use for data transmission. So first, let's understand the early days. Back then, the main type was IDE. The characteristic of IDE is that it sends data simultaneously through multiple wires. The advantage is that it has a theoretically high bandwidth, but in practical applications, it suffers from significant signal interference due to the multiple wires. This interference prevents the frequency from being increased, which ultimately led to its obsolescence. Next, what are the ports we are using now? You may have heard of them, right? There are SATA, SATA port, SAS, and NME. NME is a relatively new type. It is mainly used for transmission on the solid-state drive, data transmission on the solid-state drive, and this is our main one. The characteristic is that it operates on a single channel, Shumao. Even though it used to be multi-channel, now it's single channel, which actually allows for faster data speeds and higher frequencies. Plus, since there's only one channel, there won't be any signal interference, making it more resistant to interference, so the speed far exceeds that of traditional parallel interfaces. This gives you a basic understanding of the fundamental concepts of interface protocols. Next, let's take a look at the overall development of interface protocol. First of all, we actually introduced this earlier, right? Initially, it all started with IDE. This cycle began with IDE. Well, at first, what about the IDE disk? What about its performance? Compared to now, it's already quite different. So basically, you can hardly find IDE drives in servers these days. They're very rare, almost non-existent. Now, what do we mainly use? First of all, starting from around 2004, we have SATA drives, SATA interface, SATA 1.0. Moving on. The development of SATA from here to 2008 leads us to the SATA 3.0 version. At this point, the SATA interface has basically reached its limit. The updates have basically stopped. Moving on to the next part. Our SAS connection, and then the SATA interface connecting to SAS. The next one is SAS. SAS has actually seen updates all the way up to 2017. So as of now, it has been around since roughly 2012. This one, over the past decade or so, has become the most useful type of storage, or we should call it an interface type, an interface protocol. This has completely changed our overall storage structure. Because right now, we're focusing on real-time computing, and of course AI as well, real-time computing, including various aspects of AI. The rise of different scenarios means that our storage interfaces need to keep up with speed. Hard drives are getting faster, right? Memory is also getting faster, so this cable in between can't lag behind. If this cable can't keep up, it's going to be a problem for us in the end. It definitely has to be the hard drive connected to our memory through this cable. Originally, our transmission is through this line. If you can't keep up with the interface protocol, right? If your transmission speed is not enough, you will easily drag down the hard disk and memory down. So the requirements here are actually quite high. For us as a whole, the reading and writing requirements are very high, so we are here. Regarding the follow-up, the SATA interface is being used less frequently. It's not extinct, just like IDE, which is mostly obsolete. SATA still exists. If read-write needs aren't high, SATA and SAS are fine, especially for mechanical drives. We're just storing data, so SATA suffices. NVMe isn't necessary. NVMe offers higher speeds and is optimized for flash storage, enhancing high-speed disk performance. It doesn't matter, especially if you are connecting a mechanical hard disk, right? We just want to store data. Then SATA SAT is enough. There is no need to use NIE. In fact, its read and write speed is right. It can. What can it do? And what does NV specifically target? We have made some optimizations for our flash memory. We have made some optimizations for flash memory, for our storage memory, and for these high-speed disks. We have made some special optimizations for these high-speed disks so that we can make this. The speed is impressive. Why? Our speeds, whether flash storage or storage class memory, are close to traditional memory. With supportive connections, the speed increases significantly. This is our focus. Looking ahead, there's NVMe over Fabrics, NVMe OF, an extended version of high-performance NVMe for the network layer. It supports transmission methods like fiber channel and Ethernet, moving beyond local disks to network-level transmission. Next, we'll introduce our latest developments. The characteristics of NVMe, right? Yeah. Now, aside from NVMe, as we move forward, you can see that there's an NVMe off version, such as NVMe over Fabrics, for example. This is an extended version. Where does the extended version extend the high performance of our NIV? It extends to the network layer. It supports multiple transmission methods, such as FC and Ethernet. It is not just a local disk. It adds some network factors and some transmissions at the network layer. Here we will mainly introduce our latest and these two versions. These two versions. In traditional architectures, it's mainly based on SAS, focusing on SATA and SAS. As for NVMe, it connects directly to our CPU through the PCIe interface. This way, our path is shorter and the latency is lower. That's one of its key features. In contrast, traditional SAS connects through a controller. First, it goes through the SAS controller, then it gets forwarded through layers before reaching our memory and CPU. But with NVMe, it's a direct connection via the PCIe interface. You can see here that SAS operates differently. It can connect directly to our CPU, which means our path is shorter and the latency is lower. That's one of its key features. Traditional SAS, on the other hand, operates through a controller. First, it goes through the SAS controller. Then, it's forwarded through various layers before reaching our memory and CPU. But with NVMe, it's a direct connection via the PCIe interface. Everyone can take a look over here at the SAS side, which looks like this. It goes through multiple layers of controllers to reach the CPU. Well, here we go directly. That's actually its first advantage. That's its first advantage. The second advantage is our NVIE support. A queue depth of 64K. And each queue can independently handle requests, allowing it to fully utilize multi-core CPUs and the capabilities of flash storage. But for SAS, it only has a depth of 256. NVMe supports a queue depth of 64K, which is $64,000, while SAS only has 256. The difference is really significant. It's a huge gap. Secondly, in this area. Well, in the context of network scenarios, specifically in our particular setting, what we're looking at here is, this includes our second version of NVMe over Fabrics. The second version encapsulates our NVMe commands into FC, TCP, and RDMA networks to achieve remote storage access. For instance, this is particularly useful in AI training scenarios. Multiple servers can share the same high-performance storage pool. Through our solution, which is one of the main features of our application scenarios. Let me give a specific real-world example. Taking Huawei's storage as an example, we support 6. 104 GFC and 400 GRI Ethernet can provide enterprises with storage services with microsecond latency. It is also suitable for high-frequency financial transactions, including real-time processing of medical images and other scenarios. This is us. That's the main content for today. Alright, that's it for today's discussion. If anyone wants to learn about Huawei's cognitive technology or wants to access the Huawei certification question bank, please feel free to message me or leave a comment below the video for discussion. So that's it for today. Everyone, bye.